Musa Idris Tanimu. Thank you, Kristen, and everyone. You're welcome. My name is Musa Idris Tanimu. I'm a research student from University Kuala Lumpur, Malaysia. What we'll be talking about today, sharing today, is about the effect of pyrolysis temperature on the labile content of lignin chars derived from oil palm, empty fruit bunch, and commercial kraft lignin. We are going to be doing carrying out our studies with proximate analysis and FTIR.
Sorry, Musa, can you go in presentation mode so we can see it full screen? Yeah. Thank you very much.
Yeah, so my supervisor is Professor Robert Thomas Bachman, and my co-supervisor is Dr. Low. He's from the Malaysia Palm Oil Board. First of all, the motivation for this study is that we all know that when chars are put in anaerobic digesters, they tend to enhance the yield of gas, biogas especially, and also it helps the stability of the overall stability of the digesters. So a lot of theories have been proposed, like for the reason for increased yield of biogas. One of them is ammonium adsorption. Some also said it is as a result of acid stress relief within the digester. Some explain that it is the electron shuttling of biofilm formation on biochar surface, which accelerates the methanogenesis process. And of course, the methanogenic process is methanogenesis is the last of the stages. So, but of course, there are other stages before that. Then others said it is as a result of biomass immobilization. So there are a lot of theories about this, and it is not really understood the mechanism of why chars actually give higher yield. And so more often than not, most of the time, chars that are used are made from whole biomass. Like when you talk about, say, wood, for example, which consists of lignin, cellulose, and hemicellulose, they are all carbonized as a whole. And the chars are used. Normally, that is how chars are produced. But because of the fundamental nature of our research and the fact that we want to know what is this mechanism all about, we want to really know what is contributing, what is responsible for this increased production in biogas, we have decided that we will separate these biomasses into lignin, cellulose, and hemicellulose. And so today I'll be discussing with you how the use of, the motivation is for us to use lignin char, cellulose char, hemicellulose char separately in different digestions, so that we will actually be able to study in detail what is really responsible for this increase in yield of gases. But for today, we'll be talking about lignin char. Actually, we obtain our lignin from oil palm empty fruit bunch. As you all know, Malaysia is rich in palm oil plantation. Is the mainstay of the country, and empty fruit bunch is a kind of waste which could be put to good use. And of course, like any other biomass, it contains cellulose, hemicellulose, and lignin. And so we isolated our biomass, our lignin from empty fruit bunch, and then from there we carbonized using the ASTM method. After extracting our empty fruit bunch, we got our lignin. After, first of all, getting our EFB, which is the empty fruit bunch, we carried out extractive removal, about 32 cycles of extraction according to ASTM with ethanol toluene mixture, as well as ethanol and then water. And then after drying, we further we extracted our lignin from EFB according to the same ASTM standard 1106. So what I'll be discussing today is the result of carbonizing the chars that we have obtained from lignin. So the lignin we extracted were charred at 3 different temperatures using TGA, thermogravimetric analysis machine. So we had Tori char, which was carbonized at 250 degrees Celsius. We also have another one carbonized at 400 degrees Celsius, which we refer to as pyro char. And then the third one was carbonized at 750 degrees Celsius, which we refer to as gassy char. So these chars proximate analysis were carried out on these chars, and the result of proximate analysis is what we can see on the screen currently. First of all, you can see the weight loss curve. In this figure 1, you can see the weight loss curve in dotted lines of Tori, pyro, and gassy char. The solid line is a temperature profile, which refers to the secondary axis there. So you can see that there was a loss of mass with time as well as with temperature. So in the second diagram, in the second graph, we have the TGA for commercial lignin. That is the proximate for commercial lignin also. So we're trying to, the commercial lignin is coming in now because we need, if we are going to be digesting the chars from lignin, we need a sort of positive control to be able to compare with our char. And what is widely available is the commercial lignin, which is sold by Sigma Aldrich. So the commercial lignin, the one we bought from the market, is what we refer to as the commercial lignin here. It is also known as kraft lignin. So we will need to compare these two because, first of all, we need to know whether the commercial lignin can serve as positive control, an adequate positive control. And we can only know that by characterization. So from our proximate analysis results, we can see in figure 3 that our EFB lignin and that of the result for volatile matter versus temperature for our EFB lignin and that of commercial lignin in comparison with literature. So we can see that our EFB lignin has gave up more our commercial lignin. You know, our EFB lignin is quite better than our commercial lignin because you'll find out that if you look at the graph now of volatile matter versus temperature, you'll find out that in both cases, the volatile matter decreases with temperature. So even though they follow the same pattern, but we can find out that there is more volatiles in the commercial lignin than in our EFB lignin. So the table 1 shows the ash content of chars in comparison. The commercial lignin can be seen from these figures, from the figures obtained for ash content. We can see that the commercial lignin char has more ash, is richer in ash than the EFB lignin. And you can see that the difference is so much, where you have in the original lignin, you have 20.2% of ash for the commercial lignin in the original one. Then in our own EFB lignin, we have 3%. There is wide variation. So these two lignins, it shows that these two lignins, probably because they are from different sources, of course, we expect that they will have different, they are likely to be different or even different in ash content. So in table 2, we have the fixed carbon. You can see that the fixed carbon also for our EFB lignin is quite higher than the commercial lignin. And so it therefore means that our EFB lignin is much more stable, much more stable than the commercial lignin that we want to use. We bought the commercial lignin in. So therefore, okay, from these results now, we can see that these two lignins are not the same thing. And the commercial lignin might not really be an adequate positive control that we can use for our studies, because there is wide variation. And this variation also means that these lignins are from different sources. From all indication, we have different classes of lignin, lignin from softwood sources, which are known as gymnosperms, from hardwood sources, which are known as dicotyledonous angiosperms, and so on. So from all indication, but for EFB lignin, for EFB belongs to the class of hardwood dicotyledonous angiosperm. And so the commercial lignin must belong to another type of variant of lignin, probably from softwood. It is suspected that maybe it is made from beechwood, even though it is not quoted in the data sheet, but probably it is made from a beechwood, and so that brings the variation between the two. Then we went on to carry out FTIR, FTIR of the chars, both the commercial lignin and the EFB lignin, as well as the chars. In this place is a sample FTIR for Tori char, for commercial lignin, pyrochar, and gassy char. You can see the similarities in the FTIR, except that the functional group as well as the quantities might differ. And because of that, we have to go on to do deconvolution in order to be able to calculate certain labile contents. For chars, there are certain labile contents we are expecting, especially for our own purpose, where we want to use it for in digestion, in anaerobic digestion. So we are expecting that the aliphatic components will decrease with time, with digestion time. And so our main interest is to look into the aliphatic to see how the degradation of the aliphatic components will be relative to the aromatic components. We all know that when chars are formed, as temperatures increase, they become much more aromatic in nature. So our interest is to see, look at the ratio of the aliphatic to aromatic as these chars are carbonized. So we went on to carry out deconvolution and of the spectra, and we were able to come up with the different functional groups that are available in each of the each of the char type, both for, that is, gassy char, pyrochar, and tori char. As I've said before, gassy char was pyrolyzed at 750 degrees Celsius, and the pyrochar was pyrolyzed at 400 degrees Celsius, and tori char at 250 degrees Celsius. Our interest mainly in this, in the functional groups that we are looking for, the labile contents that are of interest to us, are the aromatic contents as well as the aliphatic. And the aliphatic content that will be of interest is the 2,800 and 2,900 per centimeter functional groups, which is mainly the CH asymmetric stretching of side chains. And as well as then the aromatic components that we are interested in are those ones from 1500 to 1560, which are mainly due to aromatic skeletal vibration in the char. So as I've said, of course, we expect that the char will become much more aromatic with increase in temperature. But we also know that the labile contents in char, though small, but they are reactive also. So we seek to use this labile content in char digestion. During the digestion, we are expecting that some of these labile content will be the first to digest. And so if there is a digestion, it also means that there will be gas formation. At least there will be some biogas formation. And if there is biogas formation, then that is a proof that there is the chars are loaded with labile contents that can be degraded. We went further for these two chars to look at preliminarily to look at the aliphatic to aromatic, to compare the aliphatic to aromatic ratios. So from the first table here, you can find, we talked about, from the convoluted spectra, we got the intensities for each type of char, especially for the 2,800 and 2,900 region. wave number region. So for the different chars, that is empty fruit bunch char and commercial lignin char, we're able to get the intensities for each of them. And you can see that by dividing the ratio of the intensities of the CH region with that for the CC double bond region, which is the aromatic skeletal vibration, mainly known as the aromatic skeletal vibration, which is used as marker for aromatic components in chars. So this type of comparison was done by Budai et al. And it states that the ratio of the intensity of the CH region to that of the aromatic region is a fair way of analyzing and measuring the aromaticity of the char. In this case, the aliphatic to aromatic component. So from the results, you can see that in comparison of the commercial lignin, which is the CLC here, with the EFB char, we can see that the toric char has 0.15 aliphatic to aromatic ratio at temperature 250 degrees Celsius. And for pyrochar, the ratio decreased at 400 degrees Celsius to 0.1. And at 750, it further decreased to 0.02. That is for the empty fruit bunch lignin obtained from the char obtained from lignin, which was extracted from oil palm empty fruit bunch. In the second column here, we have the commercial lignin char. And the ratio, we can see instead of reducing, actually increased. And then to a high point. In other words, during the toric char at 250 degrees Celsius for the char that was carbonized at 250 degrees Celsius, the ratio was 0.15. And then at 400, for the char that was pyrolyzed at 400 degrees Celsius, which is the pyro char, the ratio increased to 0.72. And then lastly, at 750, it reduced again. It does look like these two chars have different labile contents. First of all, we can see from the proximate analysis result that the ash content is quite high. And if the ash content is high, it might not be a good comparison with our own char because they are not within the same range. And during anaerobic digestion, it is possible that most of what is responsible for ash is metallic ions, and that could go on to catalyze the anaerobic digestion reaction. And that may not be able to help us to know really the true position of the labile content in the chars. So I believe that the commercial lignin char having a lot of volatile components at the beginning at 250 degrees Celsius, most of the linkages, like the aliphatic linkages, the CH linkages, begin to dissociate from the parent chain. And so they accumulate at 400. That is why you find that you have more aliphatic at 400 degrees Celsius. And so when the temperature is taken further to 750, those side chains that are broken away begin to react within the char again to form other components. And of course, we know the end of the end result of chars, the end component is normally the polycyclic aromatic hydrocarbons. So with this result, it shows that the commercial lignin char is not really an adequate, cannot adequately be used as positive control in our test. And it might not be, it might not really, it cannot, since it cannot be used, so it might not really be a good way of assessing the quality of the lignin that we have. So the results also show that the EFB lignin is much more stable than the commercial lignin char, because you can see that the result of the fixed carbon shows that the EFB lignin char is has higher fixed carbon than the commercial lignin char. Thank you.
Thank you, Musa, for your presentation. If anyone has a question, we have time for 1 or 2 questions. Please write them in the chat or just ask directly to the speaker. You can unmute yourself. Maybe first a question from myself. Did you experience any problems with the FTIR spectra for the gassy char, you call it? Did you get a lot of adsorbance, or?
You mean the spectra for gassy char?
Yeah. Did you get a nice baseline, or did you get issues with actually?
Yes. The baseline. Yes. First of all, collecting the spectra was a Herculean task, because you will have to try several times before you can even get a good spectra. For gassy char, it was very, very difficult getting a good spectra. And it is even further much more difficult to analyze when you are doing your deconvolution because of the noise. You have a lot of noise in the spectra, and then depending on your noise setting and the setting of what you are using. For example, the software you are using. I am using Omnic from Thermo Fisher. So depending on the algorithm also, you might not really be able to get a very good deconvoluted spectra. But we managed to get, after several repeats, we managed to get a good, and it is, you can see from here, from our deconvoluted spectra, these are the regions for 2,800 to 3,800. This is for gassy char. As you can see a lot of noise around here, you know. So the software also responds to noise as well, and you can see from the second derivative spectra here, you have more noise wherever you have more peaks here where you have noise. So you will have to use a lot of discretion to, and also guided by literature, to be able to know whether you have gotten a very good result.
Okay. And the last question from Hugh, how did you measure the proximate analysis data? I'm not sure, but maybe he was looking at a slightly upward curve in the proximate analysis.
Okay. This? Is it this?
Hugh, can you?
This?
I think
Yeah, that's that. Did you use the instrument, or did you do the muffle furnace where you put it on the edge for a few minutes and then ash it out? This is the data I'm interested in knowing. It looks like it was collected on the instrument.
Well, this data was obtained and then analyzed using Excel. We collected the data from the machine, and then
we use TGA.
Yeah, TGA. This is all done. So the initial 950, you're taking the about 80 minutes to 120, that amount. And then you're going, and it looks like you're then ashing it at 750. You went to oxygen at 120, or you opened it up and then got it that way.
Yeah, this other part, this one, I said the solid line here, sorry. The solid line here is the temperature profile of the TGA, and it refers to this temperature axis. Now, what happens here is that during the first heating to drying, there is a holding temperature for drying. And then during the second phase of heating, after it was heated to about 900 degrees Celsius and then held again briefly for about 10 to 15 minutes. And then after then, air was used. Air was introduced to burn off the residue.
I think we used the air at 600 degrees after the temperature dropped to 600.
What is the sequence of curves on the left? Which is the Tory char and which is the gassy char?
Okay, this is the Tory char, this is the pyro char in the middle, and this is the gassy char. So this is the, yeah.
Okay, I would say we have to stop now because we are a little bit late on time already. And usually we want to stop shortly after 1 hour. So thank you very much, Musa.
Thank you.
Thank you. Good talk. Very well.
Yeah,
Carry on.